All right, moment of inertia for a uniform sphere. So let's see, get our axes out there. This one's a little bit trickier. We're going around our z-axis. We have our x and our y, and there's going to be this spherical shape here. We are going to build the spherical shape out of a bunch of disks. And the reason why we're choosing to do this, moment of inertia obeys superposition. So let me type the rest out. This is going to get messy if I try and write fast. So if we add up the moment of inertias, for small pieces of a shape like a sphere, we can get the inertia of the whole shape. So we're going to think about that disk is our di. Moment of inertia of that disk will be 1/2 mr squared, in this case dm, because we want the mass of just that one disk. So it would look something like this for the moment of inertia of the pink shape. Then we're going to add up all of those to find our final moment of inertia. We still need to think about dm. All right, first we need the density of the material. It will be m divided by the volume of the whole sphere. That will look like 3m over 4 pi r cubed, where r is the big R, it's the radius of the whole sphere. So here we have m over v to get that density, and that will be equal to dm over dv. So dm is going to be 3m over 4 pi full radius cubed times the volume of our disk. The volume of the disk is pretty easy. It's going to be the area of the disk times its height, which we will call dz. Okay. That means we need to relate r and z. So dz, that vertical axis, if we look at a projection of the whole shape here, we've got r along one side, we've got z along the other, and we know through the diagonal. Let me make this drawing way bigger. Right, there we go. So here, along the line through the middle, there's the center. We're going to look at some particular height where we have radius r. To get there, we have to go up some distance z, and the distance through the center is r, so we know that big R squared is equal to little r squared plus z squared, which means we can write little r squared in terms of z squared as big R squared, the full radius of the sphere, minus z squared. That's the way I'm going to choose to do it here. So that means dv is pi. Actually, I went to do dm at this point. That means dm will be 3m over 4 pi full radius cubed times pi times full radius squared minus z squared dz. And we can cancel out that pi. All right. When we find I, it's an integral over all the individual di's. So integral over 1/2 r squared dm, which is going to be an integral over 1/2 r squared And then we get our dm, 3m over 4 full radius cubed. And, you know, I shouldn't have bothered substituting in for the little r squared because hopefully you see we're going to have to do it again. All right, so to wrap up. All right, we're integrating over z. Z goes from minus r to r. It goes from the bottom. If this is 0, 0, 0, it goes from right here, minus r to the top, plus r. Okay, so integral minus r to plus r of 1/2 big R squared minus z squared, 3m over 4r cubed, full R squared minus z squared dz. Oops. Minus r to r. Let's take the constants together. 3m over 8r cubed. We'll take this stuff together, minus r squared minus z squared squared, and dz. This looks like it's going to be a symmetric integral, so we'll make the change to 2 integral from 0 to r. Keep our constants. Let's square the whole thing out there. We get r to the 4th minus 2r squared z squared plus z to the 4th and dz. We'll be able to cancel a 2 there. So integral from 0 to r. The 3m over 4r cubed could come out in front. R to the 4th minus 2r squared z squared plus z to the 4th dz. All right, we're going to get r to the 4th times z minus 2r squared z cubed over 3 and plus z to the 5th over 5 in our limit from 0 to r. All right, so 3m over 4r cubed. Then we get r to the 5th minus 2/3 r to the 5th plus r to the 5th over 5. Let's go ahead and cancel out the r's. We'll get a bunch of r squareds. Those can come out in front. 3mr squared over 4. The remainders, we have 1 over 1, minus 2 over 3, and plus 1 over 5. Those have a common denominator of 15, so we have 15 minus 10 plus 3 all over 15. So 3mr squared over 4. 15 minus 10, 5, that's 8/15. We can do some cancellation. Oops, that's going to be a 2 and a 5. And we get to 5ths mr squared for a sphere. Okay. That was a longer one than most of them have been. We do have one more cool one coming up, but first we're going to have to handle parallel axis theorem. And then once we have parallel axis theorem in hand, we will do the rectangular plate. Okay, so that will wrap up the chapter. Let's get those two done.